In this lecture, we're diving into the authoring portion of blockchain consensus models. Broadly speaking, consensus is a decision-making process that aims to reach an agreement among all participants. For example, let's say we want to decide where to go out tomorrow night. Not everyone will have the same preference, but we'll eventually agree on a destination. Even if it's not your top choice, you still acknowledge that this is the group's decision. In blockchain, consensus operates similarly, but participants are computers and might be on different sides of the globe. The agreement here is on the shared history of the state machine, specifically the one every network participant deems real. The input to the system are user transactions, while the output are blocks that contain those transactions. High-quality block space relies on strong incentive alignments and guarantees. As we'll learn, not all blockchains generate block space the same way, and there's always a trade-off between decentralization and performance. Let's talk about the different layers of consensus. There are multiple ways to view this, but I like to think of these as layers that help filter out possible blockchain histories until we converge on just one. We will go through them in order: state machine validity, political validity, right to author, and fork choice. First, let's discuss state machine validity. This checks if the history of transactions in the blockchain is valid. For instance, imagine a light switch state machine, where the switch goes from on to off, or from off to on. If the history shows an invalid state transition, such as on to on, we discard the blockchain. It's simple. If the state machine isn't valid, the blockchain isn't valid either. The next layer is the political validity. This means we might reject blocks that don't meet certain political or arbitrary rules. For example, in Bitcoin, blocks bigger than 1 megabyte are discarded. Another example could be censoring blocks that contain transactions from controversial apps like Tornado Cash. The third layer is concerned with the right to author. In real-world blockchains like Ethereum or Polkadot, there are restrictions on who can author blocks. You might wonder, why? Isn't this supposed to be permissionless? Well, imagine if anyone could author blocks at any time. The result would be chaos, blocks coming in too fast for anyone to process. To avoid this, we throttle block authoring to ensure the system can sync properly. This is where leader election comes in. Leader election is the process of choosing who gets to author the next block. This is similar to what happens in traditional replicated databases, except that in blockchain, the leaders are cryptographically identifiable. Who is the current leader, that is, has the right to author when, is one of the key differences between different block authoring mechanisms. The concept of liveness comes in here too. Liveness means the ability of the system to keep producing new blocks. It's like a system's uptime. We want the blockchain to keep running and stay online. The way block authoring rights are structured impacts liveness. For example, what happens when someone is selected as leader but does not produce a block? The last layer is the fork choice rule. In case different nodes build different blocks, for example, if the network splits for some time, there needs to be some way for future block builders to determine which fork is the canonical one. Every node calculates its own view of the blockchain and decides which chain to follow based on the fork choice rule. If new blocks make a different chain the canonical one, according to the fork choice rule, a reorganization occurs and the blockchain history adjusts. Reorganizations can be frustrating when transactions are dropped, but they're a normal part of keeping the blockchain consensus.